Today we'll just be going over a little brief coding session about implementing a new boundary condition within the turbo machinery architecture in SU2. My name's Josh. I work with the SU2 turbo guys. I've been doing it for about a year now. There's my email if you want to pester me with any questions after this. So firstly, we're just going to start with what this workshop is. So first and foremost, it's an introduction to the development of SU2. So for some of you guys at the front, Toby and Tom, this might not be too relevant for you guys, considering you probably, this is way above, or more importantly, critique my coding. But for someone who is, say, a user of SU2 and thinks, oh, I really want to add this feature in to make it better, hopefully this will give you a brief introduction of at least the method I take and try and implement when developing it. So hopefully we'll try and build a little bit on what Pedro spoke about at the very start. This is going to be an example case for users wishing to develop turbo machinery specific features. So we're going to be looking at the Giles boundary conditions that we spoke about all day today, and like a little use of the turbo vertex structure that we've also spoken about today. And then finally, it's going to be an interactive tutorial for again, providing a really good starting point for any prospective developers and users. What this workshop is not is a C++ course, lesson, lecture. It's a lovely Wednesday, sunny afternoon. I don't think anyone wants that. It's not going to be particularly advanced. It's not going to be a highly detailed analysis of the SU2 code base. It's just going to be a brief introduction, okay? And then it's also not going to be a particularly comprehensive guide for turbo machinery specific elements of SU2. Okay, so with that being said, let's first do some housekeeping. So again, we're going to be using the new turbo outputs branch. I think I compiled with the debug flags. The reason for this is because, and the reason we've been using it today is because some of the changes that we've made in here will hopefully in a few months' time go into develop and then onto master. So in a few months' time, if we come back to this, it's not going to be all completely wrong. Okay, we're going to be using the same test case as the CFD tutorials by Ali and Ashwin. And then also, if you have any questions, just stick your hand up and ask me throughout. If you get a bit lost, feel free to interrupt. Okay, so our agenda. First, we're going to talk about our problem summary. So mass flow boundary condition. Talk a little bit, little recap on the Giles boundary condition and the turbo vertex structure. I'm going to do an even briefer recap of the code overview and the relevant classes for our application, the required modifications, and then we're going to go in and look at Visual Studio, type some code, and hopefully get something running. So first things first, our problem summary. So we want to implement a mass flow outlet boundary condition. So why might we want to do that? Mass flow outlet conditions, you'll find them in almost all CFD solvers. They're really, really useful. They allow you to prescribe to the mass flow of the outlet, which often can result in some better conversion stability compared to static pressure boundary conditions, and also allows you to give a little bit of directional control for the flow of the outlet, which can be important for turbo machinery stuff. So again, we'll move on. We'll go into fly straight past that. We'll go into the Giles boundary condition and the turbo vertex structure. So the Giles boundary condition is a non-reflective characteristic boundary condition implemented in SU2, as we've just talked about this morning. It's really, really simple for outflows. The maths behind it is very complex, as I was talking about this morning. But for outflows, it's really, really simple. We only need to calculate one change in characteristic variable, which is called delta C4. And this is the only one that's specified in the outflow. So we calculate like this, and then to calculate that fourth characteristic variable, we use this equation. So this is the equation that you'll see pop up as in our code. So to calculate a characteristic jump, we need to obtain the required change in pressure at the outlet. So we can do this two ways. The first way that I put here is by taking your average pressure at your outlet and multiplying it by some factor K and the difference between the average mass flow that you calculate and the mass flow rate that the user prescribes. This then Sorry, I'm just going to mute that. This then goes back into our character jump equation, and we get the required, and we then prescribe some mass flow boundary condition here. However, this requires some factor K that the user gives, and in my opinion, it's very ambiguous, and it offers a lot of areas to mess up. You can either set this too small, and it's going to do nothing, or you can set it too large, and it's going to crash your simulation. And there's no real effective guidelines. It all works on a case-by-case basis. So I've got this other method that I like to use based on Bernoulli's principle. So we take this, we have exactly the same here. We have some average pressure calculated, and we want some change in pressure to calculate it. And if we use Bernoulli's principle for compressible flow, we can get this nice little equation here for the change in pressure. All this does is, this is in the exact same form as before with a K, but it just varies the factor K based on your flow conditions. Okay, so this is what I'll do. Well, first thing we'll do is we'll implement the K one as a nice simple demonstration, and then we'll go on to adding this, which is a bit more complex. Okay. So the turbo vertex structure that Matteo was talking about earlier, we have our nodes or orders on our span-wide band, which is this little red line here, and then we have our band across in the blue, and the characteristic is jump is calculated along each span-wise band, and this is what updates between our interface at the outflow. Our characteristic jump is characterized as an average and a characteristic component. This is again what Matteo was talking about earlier. For any more details on that, I'll direct you towards Salvo's paper. That's a very detailed explanation for those of you who want to really go in depth into the maths behind it, but I think it's probably a bit out of the scope of this presentation. And our quantities are here are averaged along this band. So when we go into the code, and you'll see average pressure, and then some marker, and then some band, you'll know that this is what we're talking about. Okay. So now we're going to talk briefly about the code overview. So try not tread on Pedro's toes too much from the talk earlier, but we'll talk about the things that we need. So there's two real aspects for this. We have two groups. We have the common group and the SU2 CFD group. The common group is things that are common to all of the aspects of the SU2 code. So this is your geometry. Every simulation has a geometry, and your config file and your config file class and your option structure. These we need to add in a config option for our new mass flow boundary condition so that the user can specify it. And we also need to add in the required options in the option structure so that when a user selects the option, the code can respond to that. We also then have our CFD, SU2 CFD, and as Pedro was talking about earlier, we need to find the right place to implement our modifications. So do we want it in the driver, where it's a very general, the workhorse of their simulation? Probably not really. That's not where we consider boundary conditions. Do we want it in the iteration? Also probably not, no. Or the integration. The solver, where we keep all our variables, all our schemes, all our boundary conditions, is that the right place? Probably is. We don't really want to go any further down than this. This is where we go. So the next part is how we're going to modify our config file for our Giles boundary condition. So in the code, this is what it looks like. It's a very long string. There's 9 variables in total. So if you put less than 9, it tells you it has to be divisible by 9. And this starts with 3 options. So we have the number of Giles markers provided in the code. So this is just the name of your marker, so whether it be inflow, mixing plane, outflow, etc. Then we have the kind of Giles. So kind data Giles, this is the option that you give it. So whether you want to say a total pressure condition or a mass flow outflow or a mixing plane option, this is what's stored in this first red box here. We have the Giles map. This is what tells the config parser which map to look in for your options. So it will take the kind data Giles look in the Giles map and try and match the option that you've given in the config to an existing option in the code. And then we have these Giles var1 and Giles var2, and these are the relative variables that we provide. So in the pressure, total condition pressure, temperature, the first one is the total pressure that you have at the inflow, and the second one is the total temperature of the outflow. These are just two variables that are essential for our boundary condition. These variables are then prescribed to the class through this config function here, which loops through the each marker Giles that you give, finds the variable and extracts it and saves it as Giles var1, Giles var2, etc., which we can then access as we will see later on. Okay, so the task breakdown for our mass flow boundary condition is pretty simple. So the first thing we need to do is add an option into the config file. So this already exists in the existing boundary condition, so we don't really need to do anything new. We just need to append onto what already exists. So add it to the existing boundary condition, read in the mass flow rate from our config file, and then provide the prescribed value when requested in the code, which is what we'll add in later. So what we need to do is find a way to store our variable and then access it in the solver when we need to. Then in the solver, we need to define a variable to store our mass flow rate, because at the minute it's not calculated. Why would it? It's not needed in the solver, so we don't save it. Calculate the current mass flow rate in the turbo averaging process. And then we need to do an action based on the current and prescribed value, which is our formula we saw earlier. We need to modify our pressure to achieve the required characteristic jump. Okay, so this is how our Giles process works in C Euler solver. So firstly, we have a function called turbo average process. In turbo average process, this is what this is the workhorse behind the mixing plane that we talked about earlier, the inflow that we talked about earlier. This is where everything is done. This is where we go along the band and we average all of our quantities. We calculate our average pressure, average density, everything that we need to go on and do our mixing planes and our inflows and outflows. So this is where we're going to compute the circumferential average pressure, which is called average pressure I in the code. We then, for our Giles boundary condition, for our static pressure one that we've been familiar with from our tutorial earlier, we retrieve the prescribed pressure, which is called pressure underscore E, which is what the user inputs, and then we compute the required average jump of characteristic variable delta average C at the boundary condition to achieve the prescribed pressure, which is very simple. It's just a -2 P me minus P calculated. Very simple. And this is the order that we do it in. So average pressure, and then calculate the required C, and then it goes on to do our non-reflecting stuff that is already implemented that we don't really care about for this. We don't need to modify any of that. And just for the sake of completion, this is what it does. We compute the average pressure, impose the non-reflective condition, and then compute our primitive variable drum, and then go on to compute the residual. So now let's just talk about the required modifications that we need for our boundary condition. So firstly, adding in the option into the map. Giles map and Riemann map is what is defined in our option structure. This is where all of our options are contained. So you'll see here you have the total conditions, pressure, temperature, inflow, outflow, total supersonic inflow, outflow, all these things that you might be familiar with if you've used them in the past. The mixing flow conditions, radial equilibrium, all these things. We need to add ours into the bottom here. And all this does is maps your string input to a map to a type output. This make pair creates a pair object that links the two in the memory. So so now let's talk about how we're going to modify our flow rate, our previous flow chart for a mass flow rate condition. So we're going to do the exact same thing again with the turbo average process, but what we need to do here is compute the circumferential average mass flow rate rather than the pressure. So we add in a little thing, we call that average mass flow rate. Then we need to retrieve a prescribed mass flow rate and then calculate our characteristic jump. And we can take advantage here of the existing static pressure option because the calculation is still essentially the same, apart from we need to calculate the required change in pressure to achieve a prescribed mass flow rate rather than prescribe the pressure anyway, which just goes back to the equation that we showed at the start. Does that all make sense for everyone? Yeah. So how are we going to do this? So we need to add a new variable, average mass flow rate, along each band. We need to resize and initialize this for each simulation, because every time you execute this command, you might have a different number of spans in each zone. So it needs to be resized dynamically as the simulation goes on. And then we need to store the average mass flow rate in the solver during the averaging process. Because at the minute it's calculated, but we store it in the turbo averaging process because it's the only part that needs to use it. So the mods in our boundary conditions look like this. So we extract the value from the config file definition and then compute the required change in pressure using the equation that I showed above. Okay, so if everyone is clear on that, we'll get on to try and do some coding now, and hopefully this will go nice and smoothly. So our implementation tutorial, I'm going to sit down for this because otherwise I'll be not much will end up in. So implementation tutorial. So let's begin. So first, step 1, add a config option. Step 2, extract our required variables from the solver. Step 3, initialize our new variables. Step 4, add a mass flow outlet option to our config file. And then step 5, add a mass flow outlet option, to our Giles boundary condition. And then step 5 is calculate our characteristic jump. And then hopefully we can do some simulating. So add a config option. So let's start here. So we need to map a string input equivalent to a numeric value in agreement map. So also, I'm going to change that color because no one can see that. View. Where is the change? Does anyone? In where, sorry? Oh, yeah. Oh, yeah, there we go. There we go. Hopefully that's a bit easier. Is that easier to read? Okay. There we go. That looks a bit better. Okay. So first things first, like one of the comments we said yesterday, the first time you look at this, it can be very, very daunting. So luckily, we kind of already know where we want to go. So we want to look in a config file. So we can either go straight into our config here and have a look and see where things are. Or what I like to do is if I know that I'm modifying something, like say the Giles map, I can just search Giles _ map and find it in our relative place, So here we have option structure, which is where we add the option. And then here we have our config functions. So firstly, we'll go into the option structure and add in our options. So this is quite laggy. So here's our Riemann boundary types, total conditions PT, which already exists, static pressure, which we've talked about today, and then our mixing plane options. So first thing we need to do is add in our mass flow outlet. So let's just call it mass _ flow _ outlet. And then give it some numeric value 15. Continue on with the list. So this will say that whenever we make a pair down here with our strings, and it's called later in the code, it's given the numeric value 15, which is why when you go into debugging, and you might, if any of you use GDB like I do, it'll come up as 15 in your switch case. So the next step is to add this to our map. So we need to make a pair between the string inflow and the map, string input and the map value. So this is really easy. We just make a pair object using the function make pair, and then we have mass _ flow. outlet as our string, and then mass type mass underscore flow underscore outlet as our map value. And we need to do the same here. So interestingly, what this means is you also be able to use not only this in the Giles conditions, but you'll also be able to use it in the Riemann boundary conditions as well, which if you want to go and do a frozen rotor simulation, you can do like that. So that's the first step. So now this is all fine. So that is the first step. So here, this is exactly it. Just repeat again for what we've done. So if you want to look at it in your own time or afterwards, you can see. So here we've just added the numeric value for each Riemann and Giles option, and then we've created a pair between a string input and an option in the Riemann map. We've done this for both the Giles map and the Riemann map. So next thing we need to do is extract our variables from the solver. So we need to add a virtual function for extracting our mass flow rate in the C solver class. We need to override this function then in the derived class C Euler solver, and then we need to take the variables stored in the derived class. So let's go into here. So first things first, we'll go into the solver and add our new variables. So a lot of finding your way around this code comes with experience, I think, as everyone can tell you. Yeah, okay, we can do that. But I just really wanted to show where everything exists in a tree as well, so it's sort of it's obvious. So in here, in solver here, you have all your solver classes. But actually, sorry, I'm in the wrong folder. But we need to go into solver here. Where's C solver? Here. So as far as where placing things go, maybe Toby, you could offer some advice here. But I generally just try and fit it in, extra functions fit in with the stuff that's related to that in the class. So you'll find stuff in here related to get average pressure, etc. So like get average, get average density, pressure, turbo velocity. Generally, grouping things like this together is a pretty good. You're not gonna overwrite anything, and it all kind of makes sense. So we'll add in our function. So inline virtual SU2 double, because this is the data type that we want to use. We'll call it get average mass flow. It requires, the input it's going to require is similar to this. We need the value of the marker that we're looking at. So this is an unsigned short. And then we also need the value of the span-wise band that we're averaging the mass flow over. So this is unsigned short val span. And then again, because we plan on overriding this, we can just return 0.0 like this. And then it's always good practice to add in some comments. Yeah. So we just run that in the .c processor, and you can like anything else. If you like that right stuff, we can just run with and it'll smooth everything out to make it consistent. again, with this, whenever I'm adding something new, again, just follow the existing patterns and I think you'll probably be fine. A lot of these variables are called multiple times. So like config, for example, will be called multiple times, or val mark will be called multiple times. Just sticking with the same description on the end is good practice because it's going to stop people from getting confused. And this is then the value of the average mass flow rate on the surface.
Like the dot, like camel case, and then the actual variable is like possible.
I don't know, probably.
The document part is whatever you want. I mean, I think it's just that name consistency on.
There's a few places where it'll kind of swap between camel case and then underscores, and it's.
I mean, okay, yeah, because I was thinking like you're going to do document files different from the actual variable. Yeah, it's something we did do at the beginning, which we should in hindsight is just get a strict style for game, variable games, function names. We have some, but it's not.
Okay, so now we've got our virtual function in, we can actually go into the specific place in the solver and add in our where we're going to override this function. And so, as with all the Giles boundary conditions, this is all held in the Euler solver class. Again, I think my advice here for when you're adding something new would be just to find the thing that it's related to, find where that's stored, put it in. So again, if we search get average pressure and density, we've got it here. So we'll just add it in the same place. So inline SU2 double, get average mass flow rate, which is going to take our value of unsigned short val marker, and then it's going to return our final value of average mass flow rate. Now, this is going to show an error because we've not yet defined our variable average mass flow rate. So what we need to do here is add in further at the top our value of average mass flow rate. And so you will find here a bunch of variables that do the same thing. So average flux, average pressure, these are the same points. These variables are an active matrix are where we calculate along every span, and the values are double where we calculate for each marker. So what I am going to do is just, because we only need this for each span, I'm going to call it vector SU2 double average mass flow rate. Okay, and then hopefully when we go further down to where we've just put in our function, we need to then add in our documentation, comments. So brief, provide the integral mass flow rates at the boundary of interest. You see, again, I'm just sort of following the same convention as above. There we go. So now we have our functions in our solver that's going to allow us to act as a variable. Which part, sorry? Oh, sorry, I've just copied from directly. Average. Yeah, thank you. Okay, so now that's that done. So this is what we've done. We've added our mass flow rate functions into the virtual function into C solver, and then overridden that where we then go on to use it in C Euler solver and added the required new variables for that class. So the next part is we now need to initialize our new variables. So this has a few parts. So we need new variables for the average mass flow rate across the boundary. That we need the prescribed mass flow rate given in the config file, our mass flow rate factor K, and then our required change in pressure. So the first thing we'll do is we'll do this really simple method of calculating the mass flow rate, and then we'll go into something a bit more complex. So, and then once we've done that, we need to extract the mass flow rate and surface area during the turbo average process, but that's for the second part, okay? So let's go. So the first thing we need to do is go into our function side of this rather than the file and open up C Euler solver. So at the top here, you'll see the initialization of a lot of the variables that are used throughout here, and we're going to do the exact same thing. So if we find here, we have our resizing of all our vectors that you see in the top here. So yeah, so we're going to do the same thing for our average mass flow rate. This just makes this just resizes the vector based on the number of markers that you have in your simulation. Nice and simple. Then we need to initialize it, which we can do further down here, where all this does is just loops through our now resized vector and set it to 0. So for each marker, marker in our config file, we loop through and we set our average. I spelled average wrong. Yeah, average mass. And we set the average mass flow rate value of the vector to 0 there. Nice and simple. We just pre-initialize array so that we don't get into any issues further downstream. Now we need to add our new variables to our Giles boundary condition. This file is absolutely massive. So again, what I'm going to suggest is we look for Giles here and we find out where it is. Now there's a lot of things that pop up in Giles. So what we can do is we just have a look here and see if we can find. So in the solver, BC Giles. Let's see if we can find it in Euler solver. BC underscore Giles. And we have it here. Now this is what this is where all our Giles boundary condition is handled by the solver. So here we have our pressure E, which already exists as the prescribed pressure for the static pressure boundary condition. So I'm just going to add in the new variables as we need them here. So first one we need is the prescribed mass flow rate. So we'll call that mass flow rate E. We need our factor K, which we'll call relative factor mass.
Now, before you actually start implementing the actual mass flow value condition, you get in the switch case here, like do your mass flow outlet and just like print the message or do a breakpoint there to see if and like run the case to see if like actually gets the option that you just implemented.
but it won't do anything at the minute because it's not in the switch case, but you can do that, yeah. So relative factor mass flow rate, and then we'll add in a delta P variable, which is just a change in pressure.
Also, the coding, which is, I think it comes from engine C, that to define and allocate all the memory at the top of the function, that is no longer the case, and it's no longer, it's typically recommended to send all the variables at the top. There's no search to, just allocate variables, just when we use it. So, everyone. Yeah, I think that switch to a paradigm.
Okay.
Where
In that case,
we just allocate the direction we need that. Not specifically because it's more organizing, but it cleans up the function as a whole, and it doesn't have this big block on the top where you think that they don't really know what. And another point is, I think we should, and especially this unsigned short guiding by our radar, and always allocate in the loop. That memory saving that you are, and it's your allocational. Is it?
So there are a couple of reasons why it's not the style. It's for safety. So for creating a variable, it's also a forecast. You used to put all your variables at the top of the forecast, see what you like. Do not do this. So there are two reasons I would prefer what Toby's saying. One is when you declare the variable, we would like to make it constant whenever possible, which means you cannot change this. Allocating something, it's fixed. That's much safer. Here, you're declaring small increments and you can change them anytime in the function, so it's super dangerous. Two, they're all at the top, which means their scope is this entire function. So they can change anything, which is super confusing and also might shoot yourself in the foot in all sorts of ways. If they're inside of a scope, so anytime you have a curve release, it will only live inside that scope. So always put your variables close to where they're used, if possible.
okay. In that case, we can do exactly that. We'll move on to add in the.
And by the way, not your fault by any means. This is legacy stuff, which I am just guilty of doing this in the early days. So don't put that. It's not safe.
Okay.
When you see this, everybody just
Yeah. Okay, awesome.
Meaning that there is some cleanup, but there are some of them.
Oh, yeah. Older functions from the very early days, like it's not just a minute ago. It's all.
So the paradigm elements there is not always the best way.
Yeah, I think it's written in the C++ guidelines that Pedro spoke about at the start, if I remember correctly, and I've just not followed them, but okay, we'll continue.
Much safer.
Yeah. So continuing on from there, what we'll do is we'll add in our option for our mass flow rate so we can store our variables there as suggested. If we scroll further down through this function, you'll see all these extra parts that are done. And then we'll get to this case here, which is switch config get kind data Giles market tag. This relates back to our kind data Giles variable that we input, which tells it what we want to do. So we want a total condition, do we want a mixing plane, do we want a static pressure outflow? And you'll see here as we go down, we have all the options. We have total conditions, pressure, temperature, 1D the same, mixing in and out, 1D, static pressure 1D, and these are all very long and a bit complex, but have I scrolled past to add it? I think I've scrolled past where I need to add it, I apologize. So here, after radial equilibrium, I'll put it in here, so we're in between. We add our new case, mass underscore flow underscore outlet, see it pops up nicely, and we can add in our new variables. we already have this one. Mass flow rate E, relative mass flow rate delta P. We'll leave them there for now, and we'll come back to them when we start adding in the function. The last part we need to do from the slides is we need to save our mass flow rate during the averaging process. Now, if you remember before, our averaging process is somewhere in this massive file, so we need to find it. It's called turbo average process. So in C autosolver here. This is again where all of our averaging stuff is done, and it's very, very long and very complex and very daunting to look at for the first time. But luckily, for the most part, you're probably never going to have to look at this unless you want to understand precisely what's going on. So if you're ever bored, on a weekend, then you can do this. We just need to find a place to store our average mass flow rate over a prescribed boundary. So if we scroll through, we can sort of have a look and see what's going on. So here we're doing our initialization again. Here we're looping over all of our turbo machinery markers and doing our averaging process, computing our turbo velocity, calculating our total densities, total pressures, our total products that we use later on, and then we have our fluxes here. So this is the one that we're interested in here. Total flux is 0, area times density times turbo velocity, which you should all be familiar with as a mass flow rate equation. So this is where we keep it the first one. Total fluxes, and then again we do the same for our turbulent equations if we use them, and then we keep going down and we have the same again here. So
do you need to do this? Don't you just do those area density times total area velocity? So they're divided by the area squared.
So you mean we say total area because it's do you mean to in the mass flow rate take total depth? Yeah, this is what you do here. This is where it's the average quantities are calculated. So all I've done is take a step up rather than use them later on. So if we scroll a bit further down, we've got the exact same thing here, and we can find a nice, lovely space for it just after our mass flow averaging process. So here, this is what we talked about earlier, where we have your area averaging and your mixed out averaging. This all happens here, and we can find a lovely, nice little spot for it just after we've done our averaging. So let's put it here. So we'll add a little comment so we know what we're doing. Store our average mass flow rate over prescribed boundary. I think the advantage to doing it this way, Everett, is that you are storing it for a marker, for each marker. So rather than having to then outside of it extract a value from a vector, you're doing it as you calculate it for one marker, storing it, and then doing it for the next marker, rather than having to extract variables from multiple different arrays like later down the line. This is why I did it this way. So we want to store it for the last section, and a little quirk of the turbo vertex structure is that in the variables, the last spanwise section is the average for all of them. So if we have a thing where we have if the span is equal to the number of spanwise sections, this is n spanwise sections, we can save our average mass flow rate for the current marker, I marker, as the value of the total fluxes 0, which is the mass flow rate. Yeah, do we want to continue or do we want to, I know Toby's got his eye on those desserts. So we can take a little break if you'd like. Or we can continue, it's really, yeah, 10 minutes. Okay, we'll wrap it up. So to summarize what we were talking about before, so we'll go back onto the PowerPoint. So what we've done here is we've initialized our new variables, extracted the mass flow rate during the turbo averaging process, and we've done that here using the average mass flow rate, which is resized in the number of configs, and then we've initialized these variables alongside everything else, and then we've not added it in at the top. We've added it into where the function is defined. This is just an old screenshot. And then we've added our mass flow rate calculation during the averaging process. This surface area is for the more complex equation. So when we come back, we can add in our mass flow outlook conditions, which is two switch cases. There's two switch cases where you have to add this in, and then we can run our calculations. If that is a good spot to have a grab a quick coffee. Sound good? Now we're back from that quick break. Let's continue. So where were we last time? So we just added in, we'll go back. So the first thing, we added our config options here with our numeric values in the Riemann and Giles maps. Then we create that pair between our input string and our corresponding map value. Then we extract. Then we create our virtual function in the C solver class. Overrode that function in the Euler solver class, and then added the variables that were stored in the derived class. So that's what we did here. Then get average mass flow rate. Again, then we'll override it and then added in the extra required variables. So then we initialize our new variables. So we added new variables for average mass flow rate across a boundary, the prescribed mass flow rate, our mass flow rate factor K, required change in pressure, and extracted our mass flow and surface area during the average process. And this is what we did here. So we resized the vector that we just added, initialized the variable, and then we added our new variables. And unlike we didn't add it here, because thanks to the input of Tom and Toby, we added it into where it's used in the mass flow rate case in the Giles boundary condition. So, and this is where we calculate our average mass flow rate for each marker. So, next part. So we need to add two switch cases in the boundary condition Giles for the mass flow outlet. Luckily, we've already done that. So let's go into boundary condition Giles. Here. So the first one we added here, mass flow outlet, and then we stored our initial variables. And now, if we keep looking down, I mean, none of this is particularly relevant apart from in one place here, where it takes our, sorry, it's a bit further down, one place here where it takes our, no, sorry, it is here, what am I on about? One place here where we take our spatial Fourier calculations and perform them. We just need to tell it that in the case of our mass flow outlet condition to also then go on and do the spatial Fourier. So you'll see for case static pressure, etc. We have if it's a spatial Fourier, go on and do our Fourier decomposition. So here we just add case, mass, flow, outlet. That's all we need to do. Nice and simple. So we've added our two switch cases, nice and easy. And now we need to calculate our characteristic jump. So we need to add our method for calculating the required change in pressure and the equivalent characteristic jump. We'll start off with the really simple method with the Ks, if you remember from at the start. So we'll start off with this because it's really, really easy. And it's just sort of gives a nice introduction into writing some basic maths. So let's go into our place where we've just added our variables. So first things first, where is it? Here. So first things first, we need to get our prescribed mass flow rate. So this is our mass flow rate E, and this is the value that we store in our Giles var1 spot in our config file. So to access the variables in our config, we just use the config object. We use the pointer and we get the get Giles var1. This is what we use to access our Giles variables. You can see the exact same thing above here for the pressure condition. Apart from when you define it here, you define pressure, whereas here we're defining mass flow rate. So here, and then it's marker tag. So what this does is takes the, Giles underscore var1. So what this does is it looks in the config file for the first Giles variable for a given marker, and then returns that value, which in the case of a mass flow outlet condition is going to be our prescribed mass flow rate. We do the exact same thing for our factor K, which we called relative factor mass flow rate. Apart from, instead of it being Giles variable 1, it's Giles variable 2. So it's get Giles for 2, and again, we want it for the marker that we're interested in, which is where the mass flow rate outlet is applied, so marker tag. Okay, really easy. So now we have the two variables we need in this equation, which is the prescribed mass flow rate and the factor K. Now the next thing we need is the average pressure here and the average mass flow rate. So this is really simple. Because these are calculated in Euler solver, we can just access them. So let's create our new pressure variable E. Pressure underscore E is equal to that is called average pressure. This is the average pressure for the marker that you're interested in. So first we tell it average pressure, which marker we're interested in. And then we need to tell it which span-wise band we're interested in. And if you remember from earlier, one of the quirks of the turbo vortex structure is if you tell it to look in the very last span-wise band, that contains the information for the total surface. So we just call it n span-wise sections, because this will vary between 0 and then n-1 is each span, and then n span-wise sections is the total for all of them above. So we just do this, then simply type out our equation. So it's plus rel factor rel fac mass flow rate, and then again the exact same thing. We're looking for average mass flow rate for the marker that we're interested in, which is val marker, and then we might take away our prescribed mass flow rate. Mass flow rate underscore E. Really simple equation there.
Mass flow rate should be
yes, mass flow rate E. It's just a bit zoomed in, so it's kind of difficult to see. I'll be surprised if I've not made a few of those errors when we come to compile. So yeah, Really simple. Now the next part is calculate our characteristic jump. So if we look here, site pressure 1D, this is the exact same thing. We have a pressure value, our average pressure minus some prescribed pressure we've calculated. So I'll type it out, but essentially the code is exactly the same as above. So calculate characteristic. Yeah, okay, we'll just copy and paste. So it's nice and simple. So there we have our characteristic jump. You'll notice here that there's a difference for a two-dimensional case and a three-dimensional case, and that's the number of characteristic variables. In a two-dimensional case, you only have 3, and in a three-dimensional case, you have 4. So we need to make a little distinction there to assign to the correct value C. Okay, so we've done this. Let's go back to where we were. So we've added that, calculated a characteristic jump. This has got the more advanced method. And now we just need to recompile. So this is where we see how badly I've programmed. So let's go into our build. So I have it in a folder called C new turbo outputs. I've already compiled this. I'm not going to show you how to compile. It should already be nice and simple. Really, all you need to do to recompile is just do the same function again. /ninja-c build install, and we'll say, oh, I've not saved it. So save each of the files. Oh, it's now recompiling completely. But let's see. Luckily it's quite fast on this machine. Okay, so we've got an error. Expected semicolon. Yeah, old classic. So I knew there'd be one. So this is just here. You can see it. There we go. Save that. Go again. What have we got here? So use of undeclared variable rel factor. That's not got a capital R. Where is this? In.
Just that again, you can use the terminal and VS Code. And you can
Yeah, I've always done it this way, so I didn't want to try and vary it, but you can. So again, what's gone wrong here? It's doing the same thing. Only virtual functions can be matched final, which is in HPP 1192. So this is where we did this. So this is just const, right? Or did we define it wrong here? Sorry. Yeah. Command tick.
Command shift T.
Whoa.
Yeah. Or I think it's shift T.
Oh, here. Command T. What are you looking for?
I think, oh, it's an Italian keyboard probably, or?
No.
Oh, or is it yours?
It's an English keyboard. It's a British English keyboard.
You're just looking for a terminal.
There you go.
Now, // then you add and see build install. And let's hope there's an error. And now try to shift click on the file, on the, just somewhere where. See if that works. No.
No.
Control click or something like this.
Ah,
There we go.
there we go. Thank you.
Yeah, so when you get up there, it's a what's the key to press
Command, and then clicked on. You see, when I hold command, it sort of goes to a little option, and you can click it. So the issue is there. I missed out an asterisk, so we'll apply. And then it installs, and it looks like it's done. So now I'm going to switch back to my terminal because I have it all set up here. We can just do clear SU2 underscore CFD. Yeah, and this is my config file. Just run, and it'll get going. This is a bit slow, so I had prepared. Here's one I did earlier, but we have an output file from a simulation that ran using this method for 20,000 iterations, I think. And we can, if we go down, we can see after we've got past all our initial pre-processing information, we can see our turbo performance summary, and it starts to output here. So you can notice here, we set our mass flow 0.245 in the config file, and you'll see here that we don't really start to get it at the beginning. And it takes quite a while before we get in sort of close to our prescribed value. Yeah, that's really blinding me now. I don't think it reached the things plugged in. Mine's sharing to this. Oh, actually, yeah, I can do that. Yeah, that's true. Oh, perfect. That's better. I mean, eyes just need to readjust. So you'll notice that it takes a while before we get here. And this is one of the shortcomings of the method that I described first. So now what we can do is we can try this slightly more complex method. When it wants to go in, which is this. So the first thing we need to do is we need to add in a new variable for our area of each outflow. Luckily, we can do this in the same vein as we did the mass flux, the mass flow rate, the average mass flow rate. So let's go here. So we stored the average mass flow rate in the header file for the Euler solver, which is here, right at the top. Okay, so we'll add a new vector called surface area, something like that. We then need to populate this vector for each marker, which we'll do exactly the same way we did in the average mass flow rate, and we'll do it in the turbo averaging process because that's where it's calculated. The reason why we're doing it this way and not in through the function get span in or get span out that you might also see is that this function, as soon as you start to add more cores to your simulation, it doesn't like it, and it will start returning zeros, and then everything will nan and it will break. I think the limit I worked out was something like 8 cores afterwards, and then I think it's something to do with how the mesh is partitioned. It can't access it for whatever reason. It must be a bug but rather than fix it, we could just work around it. So this is down here, where we added it. You can see here. Luckily, we have a value where we calculate our area for each, because we need it for our averaging, and we just have a value that's called total area, and this is for each marker. So very simply, what we can do is do surface area I marker equals total area, like this, nice and simple. One thing that we do need to do before I forget is resize and initialize this variable in the same way that we did with the average mass flow. So we go back to where we've added this, and we go surface area, resize, and marker. And then we can do initialization. Equals 0.0. Nice and simple. So we've initialized that, we've resized it, initialized it, and then added in the part where it's calculated. So that should be all that we need to then go back into the Giles boundary condition and add in our updated method. Now, as a few of you might have noticed, is that this equation from the compressible boundary layer compressible flow form of Bernoulli is going to fall apart as soon as you're trying to get anywhere near some transonic speeds. So a little thing that I did was add in a little if statement that says if we get over an average Mach of, say, 0.8, we can do our original method here. If not, we can do our new method. So this equation is quite long. So what I'm going to do is I'm going to create two new variables for the denominator and the numerator of this. Sorry, the other way around, numerator and the denominator of this equation. So we'll just call it SU2 double. Numerator. I might spell this wrong. So let's have a look at our equation. So we also have this factor gamma, our ratio of specific heats. This again, we need to access. So we'll add a little thing gamma. This also is stored in our config file, and it's really easily accessed by just doing config get gamma, like that.
I think this is a perfect example where you want to not have SU2 double and then variables, but because you get help from, you just get something, you use it, you don't change it. And SU2 double or const SU2 double equal or even that auto, const auto gamma is equal to that. Because the return type of config get gamma that informs auto which type has.
Yeah.
So now what you have is, you know that the scope is immutable, and even if you change at some point the implementation of the return type of config getting. So using auto helps us also to lower the refactor. And in this case, as far as I see, you can const auto.
Yeah. Is there a specific reason why you wouldn't do auto instead of doing SU2 double?
So it's just for what you're saying.
Yeah.
If you don't, let's say we change SU2 double in the future for some reason,
Okay,
All these places where it's hard to go to is SU2 double, you not have to go.
okay,
Whereas if you go to auto, and we change one of those functions in terms,
okay.
it's also shorter than you run. It obscures things a
Oh.
little bit, but.
Yeah, there's reasons why you might not want to auto. So if you know, for some reason, you know, use to get a Boolean and, you know, every time that you want to have a constant rule, is a constant auto. So
Mhm.
just that you know where it is.
Okay. Okay, thank you. So where was I? Let's close this. We'll start our equation. So we'll just do the first. We'll do the numerator here. So our numerator is going to be 0.5 multiplied. Where's the symbol? Multiplied by the average density at the marker of our interests, and then again at the last span-wise section. This is then going to be multiplied by our mass flow rate, average mass flow rate squared minus our prescribed mass flow rate. So what we can do is we can do average mass flow rate for val underscore marker, and then times that square it. Oh, it's I did the wrong thing. And then do our mass flow rate E, which our prescribed mass flow rate that we've taken from our config file. Got E. Okay, so that's our numerator. I've not included the ratio, the specific key modifier. I'll just put it in at the end, just to be easier. And then we'll do the const auto denominator. I'm going to spell this awfully. Which is just our row average times by our surface area squared. Oh.
Josh, I might have missed something.
Mm-hmm.
So it's very clear that why we have to use the constant auto to make it sense to me.
Yeah.
Why don't we have to use it also for numerator and denominator? I mean, first glance, I would say that these two numbers would be changing at each iteration. Wouldn't they? Numerator and denominator.
Yeah. When this solver is called for each iteration, as soon as it closes, everything that's in that is destroyed. And then when you call it the next time, it's recalculated. Yeah. Yeah. So once we've done with them in this function, that's it. It's over. And then the next iteration, we remake them, recalculate them, and go again. And the reason I'm doing it like this is just because it avoids a really, really long equation otherwise, which kind of is really difficult to read. So again, what we do here is we can do our average density. I've spelled average wrong again. Average density file underscore marker in span-wise sections. Multiply this by our new variable that we've just calculated, which is called surface area for our marker. And then we need to square this. So we'll just take this again and
The mistake in the first.
sorry, English is only my first language. Yeah, so I apologize. I'll just do none. I sometimes struggle with the spelling. I've spelled that's followed in there. Average density. Yeah, so we have this. And then now to calculate our delta P, which is gonna, firstly, we have our specific heat ratio function, which is gamma over gamma minus 1. We'll put another bracket around this just so it's kind of clear. And then we have times by numerator over denominator here. And then very simply, in the exact same vein as last time, pressure underscore E equals the average pressure.
This implementation is not fully general, because in case you use different differential state model.
Yeah.
That's a bigger model, then you can go down.
Yeah. So this is not, this is just for an ideal gas simulation. Yeah. Sorry, I must have missed it.
For being general,
Yeah. Okay. So, yeah, exactly. So with this, sorry, I missed one bit out there, which is span-wise sections. So with this, yeah, sorry. No, do you have a question? Okay. So where did my terminal go? What did you do? How do you open the terminal again, Toby? Oh, it's here. Here, so now we've added this, and now again, we just need to recompile, and now we find out how many mistakes I've made. Yeah, we've not declared something. I think we just saved that. What the hell is going on here? Oh, it's because we removed it. So we need to rename it const auto. This is part of the fun of always missing something. If anyone has spotted where I've gone wrong, it would be appreciated.
So on the you can in a switch. Are you in a switch?
Yeah.
So your switch has to have its own scope and final variables. So right after the case maximal outlet, put a curly and put the closing one at that before the next.
There we go. Maybe you just can't find it. Okay, so we've run that, and now we can go back to our terminal. Oh. Yeah.
So at 3 times. First of all, I think all good practice to calling where you maximum characters.
Yeah.
And I think you for example use average density dollar.
Yeah.
At least 3 times. Or I think it's, especially if you use cons, it's much easier than for the compiler if you pull that out. But this is long call, you can just call it, give it a name like average density or just density. You find it as a constant, then it's easier for the compiler to not have any, because the compiler optimizes. It will probably it might end up with the same machine code, so you don't lose it anymore. It's also kind of performance. That point you can use cons, because then the compiler knows you can never change, and it can certain organizations cannot know what they're changing.
Okay.
It might do the same, but it, the second is this whole switch statement is based on an enum, not on an enum class. And enums are not IFA in the sense that you have implicit integer. So we had in the past where people compare enums for different values in enums because what you do is you do integer comparison. But every, you already you show it because you have the enum, you add it. So that's what it actually is. So if you use natural object, what you're actually using is the integer 15. If you use the enum class, that creates a new type, which is unique. So an enum class is not you can never use a switch without being all possible cases. So that can, if you use that enum in multiple places, you might forget to create, case for your new variable. And enum class will inform you because it will error. The third thing, so we already started to switch all enums to enum class function structure, but it's a lot of work because you have to manually do it. You have to decide what to use because the current way how switches are written is that you might rely on implicit how the switch might handle your case because it might not, that might be intentional. So with enum class, you have to think about what happens. The third thing is with respect to actions. So if you go into your slides, if you go to the formula, what you here have is you introduce a new fixed point for the delta P. And the delta P, as far as I understand it, is, it's a solution to your problem. So you iterate it, and if you want to restart it, you will need that value. And so that makes the solution variable, which is a solution of which is a solution of a fixed point. And then you need to treat it the same way as the solution variable in the address. If you don't do that, you will not get correct or at all on this directory. So if you optimize, you will not succeed. Because the action in some sense now doesn't know that delta P is actually a solution variable. So when you go to the actions, when you want to do that, I did it for a string variable. You need to basically the action driver also treat this variable like a solution variable and the infrastructure error. But keep that in mind if you ever want to use that with this effect.
Yeah.
So for the meantime, if you implement that, I would do that if you use that on.
Yeah. Okay. Thank you. Yes.
I have a curiosity from I'm really interested. Is there a name convention? I understand you correctly, you were suggesting not to use too long things like average pressure.
In the average pressure, you have two accessors. And these two accessors, if you loop over these in that instance there, we don't change them. So you have like one variable that takes, I don't know, 3 characters. And then, average density allow number in yes. So that is what makes it up. And if you put up there,
Yeah.
and give it that, employ 2 instances on a thing, which you can,
Is this what you're suggesting?
Mess up and it's long, so all you got a marker and saying what sections a lot of times.
Oh. What you're suggesting is replace this with some variable.
Yeah. Because you already see if you mark that. 2 instances where you use it. It also helps if you want to change something. You only have to change once.
Yeah.
And of course, readability is the thing. So we already see. So you can of course scale it down.
Zoom out.
Those the Explorer browser and then see more. And you want to have tackle because it tells it's like doing a human like comment. They your answer is
Yeah.
So often codes or other companies, they will force you to have like 80, 100, 150 character line limit. And we can work on it a little bit if we use these simplifications like constant auto average. We don't have to overdo it, but if you have a line which has 150 characters, you might think about doing that.
There is a no or suggested ways.
So I think the 2 big ones are camel casing and snake casing, and then you see we're using that. So perfect question. Yeah. So we have story that
Yeah.
it starts with the capital N, which is will not be case, that's what I know. And the underscore E, which is our normal snake case, when you have 2 match flow rate, you would underscore flow underscore. Because 2 conventions, and often what you do is, for example, variable names get the snake case, and function names get the so when you see something, you know by count those what it is. And we never started to enforce that. We could. The problem is we have all that code, and if we start formatting that, we kill, we create so much noise in the sense that we change the code. If you pull this and you're currently under development, you have conflict because you change that code and we change that code. Now we have to resolve. And that can be very difficult. You need to be careful and do maybe chunks, so new codes are for single files. And to do it in one push is possible, but it creates, it just creates problems for other people, so we don't do it. Or we don't do that.
Another thing, Josh, I don't know here, it's also very important to pay attention on before coding on the theoretical derivation of the value. Because here, for instance, you have value switch in case the code is compressed. Because you use the Bernoulli equation, like the compressor derive the property, but remove that assumption and you generalize it completely. Then you can avoid the switch here. Probably it's more complex.
Yeah.
It really will be more complex. But you just want.
Yeah. Yeah, I agree.
So, always also, if you are aware of communication, I think that's actually fine. If you make sure that you are very specific about what is allowed. So I would prefer if you're in the conflict CUP in the conflict posture, I think it's called, that you specifically say, if natural or, if you use that natural, only the optimal these conditions.
Yeah.
And then for an error, right, only for this good model, not for this reaction. Because then the next person comes, they see the error and they follow it. It doesn't work. And the person did it, he probably knows why. So he has, instead of one to go. So I think having limitations is good. Also, that's totally fine. Probably hindering that you.
Okay. I think what's really nice about this is we've essentially just done like a live pull request where we've written some code, shipped it out to some people, got some feedback, made some changes. And this is essentially this is how the developer meetings go for like people who maybe haven't joined before.
That's also a really case, exemplary case in which the cooperate together for we improve more because for
Yeah.
0.8. Now suppose that for this case that is a certain point, equation pi, the average pi is 0.79. The pi plus 1 we have 0.81. You see?
Yeah. 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 Yeah.
And it's a good point actually, that whenever you use so-called magic numbers, so you have 0.8, it's not much invaded, or there's no clear motivation, just a little comments. I don't know, number, if you only like a number, chosen, in this case, by generalizing the expression,
Yeah. Yeah.
Like we, magic numbers, well, I don't use. Even if it's going to be a fixed constant, give it a name and put it in a constant file.
Yeah.
Unfortunately, we cannot use concept. And where concentrations
Okay. Does anyone anything else? In that case, I think we've probably reached the end of my sort of coding abilities. So again, I can go back, recompile, and run this again, and then hopefully we'll see it run and start going. Eventually. It runs quite slow on a single core. Unfortunately, there's a bit of case. Right, he's getting stuck somewhere, but okay. Here's one I prepared earlier. Again, we can see that where before we sort of struggled to enforce a mass flow boundary condition pretty quickly. I've overwritten it, damn. We get a lovely enforced condition of the 0.245 that we put at the end here. And this is hopefully what we should look out for. And so with that, we'll skip right back to the end. We've been going back and forth. We've been going back and forth. We've recompiled, debugged, and then we've also kind of, like I said before, had a sort of live sort of pull request review session. So with that, I think that's the end of it. I would really encourage anyone to get involved. It's very enjoyable. If anyone has any doubts, and hopefully if anyone has any questions about this or anything to do with the SU2 Turbo Group, feel free to drop me an email and we can get you involved. Okay, thank you.